Hey everyone, I'm Scott from Redmond PhysicsTutoring.com, and this video is part 2 of Free Body Diagram Challenge number 3. In this video, I'll show you how to set up the net torque equation and calculate the torque contributed by each force to find the unknown tension in the supporting cable. It's about time. Romeo's been waiting all week. This video starts where part 1 ended. If you haven't seen part 1, you can use the link in the description to check it out. As a quick reminder, Romeo has used a 4-foot bar at an angle of 70 degrees from the vertical wall to hold up his sign. The FBD has 5 forces, 2 hinge forces, 1 component along each axis, the weight of the bar, the weight of the sign, and the tension in the supporting cable. The next step is to write the equations for Newton's second law, which states that the net force is equal to mass times acceleration. Since force is a vector, I need to consider the x and y axes separately. Then the net force along x is equal to the mass times ax, where ax is 0 because the bar is in equilibrium. There are only 2 forces along x, Fhx and Ftbc, so this equation works out to Fhx minus Ftbc equals 0, where Ftbc is negative because it's in the opposite direction to the x-axis. Doing the same thing for the y-axis gives Fhy minus Fgbe minus Fgse is equal to 0, where the weights are negative because they're in the opposite direction to the y-axis. I haven't considered torque yet, but I'll stop for a second to see what this gets me. Fhx and Ftbc are both unknown in the first equation. In the second equation, I know the weights, but not Fhy. So at this point, I have 2 equations and 3 unknowns. I need another equation. This is where the torque comes in. The rotational form of Newton's second law states that the net torque is equal to the moment of inertia times angular acceleration. The bar is in equilibrium, so the angular acceleration is 0, and that means that the net torque is also equal to 0. So now I need to calculate the torque. I'll do this for each force one at a time and then add everything up. Tau hy is equal to rhy Fhy sine theta, where rhy is 0, so this torque is also 0. The same thing applies for tau hx, which is rhx Fhx sine theta, where rhx is equal to 0. This is the advantage of choosing the pivot point at the hinge. Tau gbe is equal to rgbe Fgbe sine of theta, where rgbe is equal to 2 feet, Fgbe is 80 pounds, and theta is 70 degrees because the angle between the bar and vertical is 70 degrees. This works out to 150.35 foot-pounds. Fgbe would tend to make the bar rotate clockwise, so this torque is 150.35 foot-pounds clockwise. At the end of part 1, I said that counterclockwise was positive for rotation, which means that tau gbe is negative because it's clockwise. Tau gse is rgse Fgse sine theta, where rgse is equal to 4 feet, Fgse is 195 pounds, and theta is again 70 degrees. It's the same angle as for the weight of the bar. This works out to a torque of 732.96 foot-pounds, and this torque is also clockwise, which is also negative. Last one. Tau tbc is equal to rtbc Ftbc sine theta, where rtbc is 3 feet, Ftbc is unknown, so I leave it as a symbol, and theta is 20 degrees. I get theta by drawing a right-angled triangle here with 70 degrees in this corner, so the angle in the other corner must be 20 degrees. I can only simplify this down to 1.03 Ftbc since Ftbc is unknown, but I can tell that increasing this force would tend to rotate the bar counterclockwise, so this torque will be positive. Now I'm ready to write the net torque equation, which adds up all the torques. Tau hy plus tau hx plus tau tbc minus tau gbe minus tau gse equals 0. You usually don't need to include the 0 torques. I'm only doing that for completeness. I substitute what I have so far and notice that there's only one unknown. This is why putting the pivot point at the hinge makes the math as simple as possible. The unknown hinge force components don't contribute to this equation at all. Making the math simple is great because it reduces the chance of making a silly mistake and you solve the problem faster. I can solve this equation to get Ftbc is equal to 861 pounds. And that's it! Romeo can now buy the right supporting cable from the hardware store. He didn't need to solve for the hinge force components at all. I'll leave that up to you, but if you'd like a preview of the answers, you should get Fhx is equal to 861 pounds and Fhy is equal to 275 pounds. I'm Scott Redmond and I help students pass physics. If this video was helpful to you, please share it with a classmate to help boost everyone's physics grade.